Okay, so quick refresher. We need a new equation. Mg and Mgh aren't going to work. Um, for some reason, I'm bringing up these weird things about your mom message or depositing money and that bringing it to zero. What we can infer about your balance if a positive deposit brought you to zero, and this whole thing about playing poker, how if you're owed money, you're trapped and not free to leave. File that away. We're going to need that after we do the math. Bit more logic before we do the math. Again, this would be a fun one to teach you for in the classroom. Energy is all about the ability to do work. So gravitationally, things have energy when they're able or have the potential to fall. So if I held a bowling ball above a hole puncher is something you have to push on to do work. The hole puncher is like a machine. If you apply a force or put some energy in by pushing down on that lever thing, then you do the job that the hole puncher is meant to do. So I just picked a hole puncher because I have one in the classroom. Hopefully it's kind of familiar with you. I picked a bowling ball because we have one in the classroom and it's kind of big and heavy. But we can use that to think about gravitational energy. If I just held the ball above the hole puncher and let it fall, falling a certain distance, because it was up high as it fell, when it hit that hole puncher, it had some energy because it was up high, and it could do work on the hole puncher. If I held it higher and let it fall farther, it could do even more work. Since it could do more work, that means that when it's higher, it has more energy. Nothing really new here. If we think back to grade 11 energy, that kind of makes sense. If we increase the H, then we're eventually going to move away from it. But if we increase the H, MGH says more energy. Okay, now we're going to start using our imagination. Imagine instead of holding the bowling ball, I got up early in the morning, had a healthy breakfast, and I threw the ball. So I used my energy to give energy to the ball, and I throw it so high that it's up where the birds are flying. It's going to stop, 9.8, it's going to turn around and come crashing into the ground. I didn't add it to the picture, but imagine little hole punchers down here. When the bowling ball crashes into the hole puncher from that high, does it do more work or less work? And more importantly, what does that tell you about the energy? Does it have more energy or less energy at that higher position? Okay, now we're getting silly. What if I take the bowling ball and I throw it high past the birds? It goes way up here to kind of the same height as the International Space Station. And then it's going to turn around. I couldn't draw it. It would look like a speck of dust down here, but there's our hole puncher. If it started off that high, if I gave it so much energy that it went that high, when it falls down on the hole puncher, is it going to do more work or less work than it did before? Doing more work or less work, what does that tell us about the gravitational field energy at that higher position? Okay, now we're getting really ridiculous. What if I throw it so high, it goes past the birds, past the International Space Station. Basically, it's almost like it's way out in space. When it gets to that point, it's so far from Earth that instead of falling at 9.8, it only falls at a rate of 5 meters per second squared. It's going to turn around. It's going to fall with a rate of 5 meters per second squared here. As it falls, we're going to ignore air resistance. So when it gets down here, back by the International Space Station, G goes back up to our used to 9.8 meters per second squared. It's going to crash into the hole puncher. Hole puncher looks like it's in the ocean in my little diagram, but whatever. Is it going to do more work or less work? Based off of that, what does that tell us about the gravitational energy? More energy or less energy? Okay, this one would be cool if we could pull this off. What if I threw it so far that when it got way out here, the G was almost 0? I just made up a number. G is 0.5. So at that moment, it's going to stop and it's going to accelerate, but it's almost going to look like it was videotaped and played back in slow motion. It's not going to fall at 9.8. It's going to fall at a fraction of 9.8. It's going to fall back down as it gets closer to Earth. The G is going to increase. It'll get back to 5. It'll get back to 9.8 when it's really close to Earth. It's going to smash into our hole puncher. We're ignoring air resistance, so it's going to obliterate our hole puncher. Is it doing more work or less work? I had to chuck it really, 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 really hard. I gave it a whole ton of energy to get it that high. And then it does more work. You follow along, hopefully. Okay, the last one. What if I throw it so far, oops, past the birds, past the International Space Station, past that point where G was 5, past that point where G was 0.5. What if I throw it so far it gets all the way to this point, and it's so far away that the effect of gravity drops to 0. It's so far away that it doesn't even really feel the gravitational influence of Earth. Our hole puncher's down here still. If the acceleration drops to 0, the effect of gravity drops to 0, when it stops, it's not going to start again. So we've thrown it so far that it doesn't fall back to Earth. I'm way down here, little stick figure, teeny tiny, I can't even draw it very well. I've given it so much energy that I get it to a point where it doesn't fall back. If we did, well, how much work does that do on the hole puncher? What does that tell us about the energy at that height? All right, going with my method of many little video clips, I'm going to pause here, think that through, and then scroll down, and we'll talk about what it means.